Hello everyone. Today I will talk about CP-Detector, a testing framework that leverages performance properties of configurations to expose performance bugs. Performance bugs are critical in applications today. Performance bugs continue to degrade performance, waste computation resources, hurt users' experience, and cause financial losses in the field. For example, 0.1 second delay in Amazon would cause 1% drop in sales. Mozilla developers fix 5 to 60 performance bugs reported by users every month. Performance bugs have caused many Firefox users to switch to another browser. But detecting performance bug is challenging. The main challenge is lacking of test oracle. Let's take an example. A user runs a SQL query in MySQL and the query takes long times to finish. The developer uses a profiler to get the execution time of each function in MySQL, as shown in this table. The slowest function is mapset, which takes several seconds to finish. However, developers cannot differentiate the slowdown is caused by a performance bug or just huge workload that is expected to consume that amount of time to finish. Actually, the slowdown is caused by a performance bug, but in this case, the software does not output any log messages nor crash, making the bug hard to be observed. Meanwhile, software today are highly configurable. They usually have hundreds of configuration options for users. The figure on the left shows the number of configuration options in the core model of some popular databases and web servers. Also, the number of configuration options is continuously rising as the software evolves. It is likely that performance bugs are related to configurations, because configurations often control the system resources software could use, such as memory and CPU cores. The figure in the left shows that the configuration options that control cache size, memory size, buffer size, concurrent thread, and etc. A recent study finds that about a half of the performance bugs are related to configurations. Meanwhile, some performance bugs only get triggered under specific configuration settings. The figure in the right shows a bug where the buggy code is right in an if section. The if condition is only satisfied when the configuration option is set to true. Note that the default value is false. Given that above, we target on configuration-related performance bug. For short, we call it CPBug. Note that this is different from a misconfiguration, which is usually caused by user's mistake. Let's see an example of real-world CPBug. In MySQL, a user do a query and set sort buffer size to a large value. The query would take a long time to finish. The sort buffer size controls memory allocated to specific query type. And the bug happens because MySQL handles the subselect inefficiently. It allocates memory of sort buffer size every time for a subselect. So if a subselect is executed many times, there would be a redundant memory allocation, which causes the performance drop. In this case, MySQL does not output any log messages, nor crash or hang. So it's hard to decide if there is a bug. However, we observe that we increase the value of sort buffer size. The query gets slower and slower. And to achieve the best performance, we need to set it to its mean value. This behavior is very counterintuitive. From the case above, we notice that the configuration option have its performance property. The performance property is the performance expectation of a configuration change. For the sort buffer size, increasing its value means allocating more system resources to software, and indicating the performance is expected to be better. So our main idea is that when the actual performance is contrary to the expected performance, in other words, it violates the performance property, they probably locate a CP bug. And we argue this counterintuitive behavior can serve as a performance test oracle to effectively expose CP bugs. To verify our observation, we conduct an empirical study on 173 CP bugs. They are from 12 mature, widely used, and performance-critical software, and the bugs are collected by heuristically searching the public bug repository. Through the study, we want to figure out whether and how can we use performance property to expose CP bugs. We term PP for performance property in the following talk. So we set these three research questions. In RQ1, we want to know if the violation of PP is prevalent enough to serve as a general test oracle. In RQ2, we want to conclude some patterns of PP that help us to design some concrete test oracle. In RQ3, we want to figure out how to change the configuration options to trigger the violation of PP. Here's the results. Fortunately, we find that violations of PP are prevalent among CP bugs. This result indicates that the violation of PP can serve as a test oracle to expose CP bugs. Then, we concluded 7 types of performance properties. Let's look at the PP4. The PP4 is allocating more resource. The performance is expected to be better, just as the motivating example we described implies. The other PPs, like PP1, is the turning on an optimization option. The performance should be better. Note that an optimization is some mechanism that is designed to improve performance. The PP2 is that sacrificing some software reliability or safety, the performance should be better. The PP3 is that enhancing software reliability or safety, the performance may have a reasonable drop. For the other PPs, the detailed description and examples can be found in the paper. And these 7 types of PP are violated by 150 CP bugs. The last column shows the distribution. Note that for violation for PP3 and PP6, the expected performance is a reasonable drop, and the actual performance is a severe drop. We conduct an empirical experiments to figure out some threshold to measure what can be a reasonable and what can be a severe. Now let's take a look at this example. This configuration option controls the level of ASE that MySQL should follow, which with lower level of ASE, the throughput is expected to be better. It has 2 values, 1, which implies higher level of ASE but bad performance, 2, which implies lower level of ASE but good performance. But in this MySQL bug, a lower level of ASE result in lower performance. This violates the option's performance property, so a CP bug is exposed. This bug is caused by false buffer sharing between 2 write events. For the third research questions, we want to figure out what values of configuration options can trigger CP bugs. Configuration options can be Boolean, enumerate, and numeric. Boolean and enumerate options have limited values, so we can iterate their values to find CP bugs. But for numeric options to obtain the values that can trigger CP bugs, we try to reproduce the related CP bugs with many values and get the result. Interestingly, we find that setting vast majority of numeric options to their min or max values can trigger the CP bug. This finding implies that we can start to testing values from mean and from the max. Based on the findings, we designed CP-Detector, a testing framework to expose CP bugs. A CP-Detector contains 3 steps. First, it infers performance properties for configuration options from configuration document. Here we use some natural language processing and association rule mining techniques to train a classifier whose labels add the performance properties. Second, it generates configuration values and runs some test cases to get the performance results. Third, it does some result analysis to detect CP bugs. I will introduce the process of CP-Detector in brief. First, given configuration document, CP-Detector uses NLP techniques to extract the syntactic and semantic knowledge of the description of configurations. Then we collect many configuration options and description, manually label them with performance property, and use existing association rule mining techniques to mine roots that exclusively appears in each type of configurations. For example, a rule can be like this. When this rule match a description, the configuration is likely to be type 3, which is allocating resources. We also add some heuristics to improve the quality of rules. The details can be found in the paper. Now we have rules for each type, so we build a voting classifier to decide the type of a given configuration option. Note that to know the complete performance property of a non-function trade-off, we also need to know which value implies anti-performance and which implies pro-performance. So we use some rules concluded by experience so to automatically ranking the values of options of this option type. The second step of CP-Detector is to generate configuration values and run test cases. Given the finding in our study, we start generate the numeric options value from both ends of their whole value range, and enlarge the sample step exponentially, as shown in the table. CP-Detector will compare the performance between 1 and 2, 1 and 3, 1 and 5, and etc. The third step is to analyze the performance result to detect if any performance property is violated. We use a concrete example to show how a CP bug is exposed. In GCC, running the workload on the left of the table and turning on this optimization option makes the program being compiled execute slower. We repeatedly execute each test 20 times to get a stable result. The result violated the performance property of this option, so a CP bug is reported. We evaluate the CP-Detector from 3 aspects. First, how accurate the CP-Detector in inferring performance property. Second, how effective of CP-Detector in exposing existing CP bugs. Third, can CP-Detector expose new CP bugs? For the first question, we randomly chose 500 configuration options from 12 software systems to train our model, and conduct a 10-fold stratified cross-validation. The result shows that the CP-Detector have good precision and recall in the dataset. We compare CP-Detector with the baseline method, which use some keywords selected by experience to do the classification. Note that the model training is one-time effort, and the training set is chosen from a diverse of software, so we believe people can use our model directly without any further labeling or training. Then we try to reproduce every CP bug among the studied CP bugs. To the best of our effort, we successfully reproduced 38 of them. To avoid overfitting, we collect and successfully reproduce 23 CP bugs and that are not included in the study. We evaluate CP-Detector on these 61 CP bugs, and we also compare the result with Toddler. The Toddler is an effective pattern-based approach to detect a performance bug that is caused by inefficient loops. CP-Detector successfully exposed 41 out of 61, 43 out of 61 CP bugs, while Toddler can only expose 6 of them. This is because Toddler only targets on a specific type of performance bugs. Last, we use CP detectors to find new CP bugs. We successfully found 13 new bugs in GCC and Clown. 10 of them has already been confirmed by the developers. These new bug cases causes significant performance degradation, and one of them even make the software hang forever. Okay, there are plenty of works target on detecting performance bugs. They can be classified into two groups. One group of work use profiling-based method to find the performance bottlenecks, but do not have a test oracle. The other group use some anti-patterns to detect performance bug. They usually target on specific type of bugs. And some works focus on optimizing performance via configuration tuning. Their target is predicting and improving performance as a whole, but not find bugs. Some empirical study has done for generic performance bugs, while the possibility that performance property can be designed as test oracle is still unstudied. To sum up, we conducted an empirical study on the 173 real-world CP bugs from 12 software, and we find performance property as configurations can be designed as test oracle. We implemented CP-Detector, an automated framework to detect CP bugs. We evaluated it on 12 software and exposed 43 out of 61 known CP bugs and find 13 new bugs.